family of young graphs are what I call the cyclic graphs. And another family that I can analyze more or less are the complete graphs. The complete graphs have the property that every node is joined to every other node, including itself. And they have the most number of edges of any young graph. The cyclic ones have the smallest number of edges of any given number of nodes. So, for example, the cyclic graphs, I must admit they're still pretty mysterious. But the definition is the cyclic graph C3 has a cycle that I've drawn in red of length 3, and there's one edge which has an extra pair of edges in parallel going to the zero node with a loop there. So the cyclic graph is a cycle plus a pair of edges. So this is C2, C3, C4, and C5. This has 1, 2, 3, 4. If we ignore the starting node, it's got 4 nodes and 1, 2, 3, 4, 5, 6 edges. These have this, another experimental fact, these have the smallest number of edges for a given number of nodes. And the unfortunate thing is, I can't explain when they occur. So the first time you see this graph is when the base is 49 and the multiplier is 16. The first time you see C3, this one, is at 1711. The first time you see 4 is at 3411. And here's the list. So for the cyclic graphs, with a cycle of length m going from 1 to 9, the first time these occur is at these values of the base, and these values of the multiplier. Now I collect sequences, and it is really annoying not to understand what this sequence is. It's totally mysterious.
And you have no proof that it goes forever.
I have no proof that it goes forever. I have a conjecture, which is on the next slide, that it does. If it does exist, if the cyclic graph does exist, then because the adjacency matrix is pretty simple, you can work out what the generating function is. And it's got a fairly simple numerator and a really simple denominator, which basically says that to get the next term, it's the sum of the previous term and the term n minus 1 steps back. And I can almost prove, well, I can almost describe what the reverse multiples are. And if this exists, then we know there is a reverse multiple that goes, so look at C4. I say, because this cyclic graph exists, there is a reverse multiple. The smallest one goes from the starting node down to the first of the possibly 2 nodes at the bottom. So here, the smallest multiple would be 2, 21, and then we go back. No, I'm sorry, this is the first example you've seen of a pair of nodes, 10, 5, and 5, 10. This is an odd pivot node. So the reverse multiple you get is 2, 21, 16, and now you go back, 32, 28. I call that number gamma. That's the number, the smallest reverse multiple, and you can read it off the graph. So that's gamma. We know it exists. Then I can almost prove that all the reverse multiples have the form gamma times beta, where the base geo-expansion of beta is palindromic. Again, it has digits 0 and 1 only, and any run of zeros must have length at least n minus 1, and there can be no repeated ones. And the argument, almost to prove that this works, is actually quite nice, I think. You can, first of all, you can look at the adjacency matrix, and you can get the denominator easily, trivially, because you know, from the characteristic polynomial of the adjacency matrix. Now, we know we have a reverse multiple, gamma, from reading it off the diagram, which we're assuming to exist. So let me do an example. The cyclic one, C3, the first example is base 17 multiplier 11. And if you read it off the diagram, you get gamma as 1, 5, 12, 14 to the base 17. Now watch what happens when we multiply by 11. So we're doing calculations mod 17. But because we can also read off the carry digits, we don't really have to work very hard. So we say 11 14s is 154, which is 9 times 17 plus 1. So the carry is 9. 11 times 12 is plus 9 is 141, which is 8 times 17 plus 5, and so on. And we get 1, 14, 12. We get 14, 12, 5, 1, which is the reverse of what we started with. So we verify directly that this is a reverse multiple. Now, the claim is that if beta doesn't have any runs of repeated ones, or any runs of zeros of length less than m minus 1, in other words, less than 2, so runs of length 2 zeros are okay. So this is a typical beta. I claim that gamma times beta is a reverse multiple. And you prove that by just doing the long multiplication table. So there's beta, and gamma, I'm assuming, is something, let me write it as A, B, C, D. In this case, it's a 4-digit number, which is on the previous slide. Now, when you do the long multiplication, you get A, B, C, D, A, B, C, D, and A, B, C, D. You add them up, and you get A, B, C, A plus D, B, C, A plus D, B, C, D. Now, we know that gamma is itself a reverse multiple. So when we multiply by k, it just reverses. If now we take k times beta times gamma, we do the same calculation, and we get the same number in the reverse order. Provided A plus D didn't overflow, we're home free. We know that the reverse is equal to the reverse, as it should be. Unfortunately, that's the conjecture. I thought I could prove it, but I have not managed to do it. The conjecture says, because we're not in the case of the 1089 graph, the sum of the first and the last digits is strictly less than the base. So there's no overflow, there's no carry when we do this addition. So we get the same tableau in reverse. If there'd been carries, this would have propagated here, and it would have messed up. It would no longer be the reverse. And so now we can... So now we have a large collection of reverse multiples by this argument, assuming the conjecture is true. Now we can enumerate them, and it's not difficult to show that we get the same generating function. I'll skip that. By direct counting, we can show that the number of these betas is equal to the numbers that come out of the generating function that we got from the adjacency matrix. So that proves, modulo that conjecture, that we've established what all of the reverse multiples are in this case for the cyclic graphs. At the other extreme, the graphs with the maximal number of edges are the complete graphs. So here's K3. Apart from the starting node, it's got 3 other nodes, and you have edges between every possible pair of nodes. So K2 is the base 5 multiply 2 example I already showed you. K3 doesn't appear until base 11 multiplier 3, and you get that. You get K4, K94, K5, and so on. And you can prove that if the base G is of the form n squared plus n minus 1, and the multiplier is n, then you get Km. And the nodes, the node labels, are all pairs RR. They have to be identical because they're all going to be even pivot nodes. You can work out what the generating function is because the adjacency matrix is just a block, a solid block of x squareds. And you can work out what the reverse multiples are. So this is a case where it's actually not so difficult to analyze everything. And the reverse multiples, the smallest one is like that example I gave of 1, 3 base 5. It generalizes to be A base G, where A and B are given by this relationship. So there's a conjecture that we get the complete graph on m nodes if and only if there are m solutions. We need a pair of numbers, b and a, that have to lie in this range. If there are m such numbers, then we get the complete graph on m nodes. So that's another conjecture. These conjectures seem really obstinate. I can prove parts of them, but not the whole thing. One thing I can prove is that you get the complete graph on m nodes if and only if all the node labels are of the form R. But what seems to be true is a much stronger fact, that if any one of the nodes has a label of the form R, then you get the complete graph. This again, I didn't say what beta is, but beta is palindromic, and it contains digits 0 through m minus 1. So this is again a palindromic case. The palindromic case is when the reverse multiples have the property that they're all of the form some constant gamma standing for GCD. It's the GCD of all the solutions times a palindromic number, beta, which usually satisfies some simple constraints. Now, here's another example. This is the 2413 Young graph. Things have gotten a lot more complicated. The generating function is, however, very simple. The smallest reverse multiple is this, of length 9, corresponding to the x to the 9th there. And again, this is palindromic. The reverse multiples are, there's a GCD, which is not the same as the smallest reverse multiple, but all the multiples are gamma times beta. Beta is, again, binary, palindromic. Every run of zeros and ones must have length at least 3. And you can easily count how many there are and check that it agrees with the thing. And as an example, the smallest reverse multiple is gamma times 111. So 111 satisfies the rules. It's got a run of length 3 of ones. So it's illegal, it's palindromic, so we get a solution. On the other hand, the 4013 Young graph looks like that. Its generating function is that, and this is not palindromic. There's no possible choice of gamma such that you can say, well, that all the reverse multiples are of the form gamma times a palindrome. And my last slide is some general remarks about properties of Young graphs. The label on an edge is determined by the labels on the nodes. There are no parallel edges. Between any two nodes, there's at most one edge. A really nice property is that if you have an edge going from a node RS to a node TU, then there's also an edge that goes from the reverse of the nodes, with a label which is the reverse of the edges. This is a very useful property. And from that you can prove that all the node labels are distinct, the edge labels are distinct. And one last thing. I haven't been able to settle the question of whether the graph itself determines the pivot nodes. This gives you an involution, because this gives a mapping. Let me go back one slide. Maybe that's hard to see. I've drawn this in such a way that you see the involution. This is the young graph. If you switch the node labels, so 5.3 to 3.5, anything with identical node labels is on the axis, and there's a symmetry that swaps the two sides. What I don't know is whether it's possible to have two different young graphs that have different pivot nodes, but have the same directed graph, the same underlying directed graph. I don't know. All right, I'll stop there.
We have 1 minute for questions.
Are those graphs, say, like planar?
No, not in general. Very often they are, but I don't know exactly when. In fact, there are many open questions. What graphs occur? How many? For a given base G, how many different Ks are there? I mean, I could give a large number of unsolved questions.
You can calculate all the graphs G up to a certain.
Up to G up to 100, with one exception, where the graph was too big. Well, I can compute the graphs.
Yeah.
The trouble is, very often there are extra edges that don't lead anywhere, dead ends. Yeah. So you have to throw them away before you can figure out what the graph really is. And some of these have huge paths that may or may not terminate. So I have a computer printer, I have a file with all the graphs, if anyone is interested.
Do you have any new from model operation, like you take the two matrices that work and then form the chronicle product or something, and you get new sequences from your ones?
I don't know. It's a good question. I haven't found anything like that. Yeah. The whole thing is extremely mysterious, actually.
Thank you very much. Today is his 74th birthday, and we're going to take him out for dinner at Evelyn's. It's okay, Evelyn?
Yes,
My wife told me that you get to pick the restaurant.
No.
Okay, Evelyn's 6:45. Like